this is Roger Green, host of the Surfing the Nash Tsunami podcast. This weekend, we are offering 4 conversations and a full extrasode from Season 3, Episode 14, our discussion on complex balloon hepatocytes, the errors they cause in drug assessment, and how AI-assisted technologies can improve analysis. This extrasode discussion lasted roughly 35 minutes, and a brief synopsis cannot do it justice. Listen to the whole thing to get the impact, and it's important and worth it. But to start, HistoIndex Chief Scientific Officer Dean Tai describes the challenges in analyzing balloon hepatocytes, which range from staining issues to systematic inconsistencies in what leading hepatopathologists might consider a balloon cell. He and Quentin Anstee describe how the approach HistoIndex used to create the Q-fibrosis analysis converted into a similar approach to ballooning, resulting in the Q-ballooning2 score. Q-ballooning2 is an algorithm for quantifying balloon hepatocyte cells. In the rest of the episode, Mazen Noureddin describes his poster of distinction from last year's AASLD, in which he used AI techniques to create what he calls a SNOF score, septa, nodules, fibrosis, to improve consistent measurement of how a drug can impact portal hypertension, determine presence or absence of varices, and frequency with which it reduces portal hypertension by 20%. As I say, you'll really want to listen to this. It's a good use of time. This issue has pivotal implications for all drug development going forward, and we all need to absorb its lessons. So sit back, listen, enjoy, learn, and when you're done, join the dialogue on our LinkedIn and Facebook discussion groups. I am fortunate to be joined by Quentin Anstee and Joern Schattenberg, who will be with us for part of this, maybe not all of it, and Mazen Noureddin and Dean Tai. Everybody, well, let's just say hi first. Quentin first. Just hi. Hello again.
Hello again.
Okay, Joern, hello again.
Hi, everyone.
Okay, Mazen, hello again.
What's up?
And then you can tell that Mazen's becoming more awake. I'll comment on that in a minute. And Dean, welcome.
Thank you for having me.
Thank you for joining us. It should be noted that it is now 6:15 in the morning in Los Angeles, where Mazen is, and I guess, 10:15 in the evening in Singapore, where Quentin and Dean happen to be. Middle of Joern's business day, and I would have been at work for an hour already today, so I'm kind of in my normal swing of things, which is good. An hour and a half even. What this portion of the conversation will focus on is the process by which we resolve what I described in the episode as taking the phrase semi-quantitative, which is how we evaluate now, shrinking the semi and increasing the quantitative so that we can become more consistent in what we do and give the idea of statistical error and consistency of results more meaning. We're going to do some of that by asking Dean to comment on that portion of the Brunt, Tai, et al. to Anstee paper that was published last year and was such an important part of NASH-TAG this year. And then I'm going to ask Joern to make comments or questions on that. And then Mazen is going to talk about the poster of distinction he put up at AASLD last year, which discussed digital pathology in the context of cirrhosis. And then we'll have more questions and comments. So with that, let me introduce our friend and colleague, Dean Tai, from HistoIndex. Dean, welcome. And please take a few minutes and walk us through that paper again with a specific point of view on what do we do to improve the quantitative nature of assessment of balloon hepatocytes, given how complex it is.
Thank you, Roger. So we started by, our aim is to develop a total solution for pathology assessment. And we actually started this work very much focused in fibrosis. And in earlier days, we were very much focused in hepatitis B and hepatitis C. And during that phase, we realized we didn't talk about this much, but the staining variability is actually a key element for pathology assessment. The fact you have many different labs coming up different colors all the time, it adds another layer of complexity in order to do a proper pathology assessment. It wasn't so much a problem when you are trying to do semi-quantitative, when you're going categorical. But by the time we are now, just like Roger said, we want to focus on quantitative and strength semi, we realize it's important to address the staining variability as well. So with that in mind, we look at NASH, and clearly everyone is talking about ballooning. So we really focus on ballooning. We have been working in fibrosis. We call it Q-fibrosis. We realize it's very important to have a proper understanding of morphology and establish a proper ground truth. So by that, we mean we need to understand what is the definition of fibrosis, what's the definition of ballooning, and exactly how they are interpreted by pathologists when they are looking at these images. So we have to take it to another level, just not look at the basic definition in like what's being written on the paper for NASH-CRN system. So this work was initiated by Quentin and Beth, and it involved more than 20 key opinion leaders in NASH, both the hepatologists and pathologists. I'm very appreciative and very happy they're all willing to help us to develop AI which we think is the future, and use this to solve an immediate problem on hand. So specifically, what we are trying to do is to evaluate intervention efficacy. So when we come in, we are really not talking about trying to come out with a diagnosis. We try to really address the need here is the intervention efficacy. Okay, and in this paper, I think we're very happy with the performance, particularly, for example, in terms of reproducibility. So we have pathologists. They can perform as good as 90% reproducibility when we rotate the images and ask them to annotate again. So the pathologist can do as good as 90%, and our AI can do this as good as 99%. And we have a ground truth. This ground truth is defined by majority of pathologists' agreement. So as explained earlier conversation, we know how variable it is when it comes to annotate the balloon hepatocytes. The solution we're providing here is really to capture the majority agreed hepatocytes with a 99% reproducibility. So this is basically what we intended in the first place. We wanted to use this to evaluate intervention efficacy. With that, we're very happy with the paper, and now we're actually moving to the next part. Trying to do the next phase is really how to use this information, how to develop a tool for the post-drug approval era. So with that, maybe I'll stop here and take on any questions or comments. Thank you.
Joern, Mazen, Quentin, any of you go ahead.
Well, Dean, congratulations again. I think we discussed the paper with Quentin previously and came out great what your team did here and how they supported this. I think you addressed the reliability, or called it the re-identification of a balloon cell by the same histopathologist, the machine with 99%, the best pathologist 90%. You didn't mention probably that it will drop lower in other histopathologists, not speaking of histopathologists that are not specifically trained for NASH. So maybe you can give us some granularity or some more information on, what's the range between histopathologists, not to say that they are not good at this, but just to get an idea. And then, one aspect is as we enroll more patients, we need more histopathologists to be involved. And what is I'm afraid it will probably introduce more variability at that level, not because the pathologist is not able to call it that way. It's just that the human system has more variability in it.
Yes, I totally agree. So you're right. There is a great variability in terms of reproducibility. So that range in our study itself, we're looking at anywhere from 40 to 90%. So as you say, is a very big range. And I maybe want to add one comment about this, because unlike fibrosis, steatosis, and inflammation, we are really differentiating a specific cell type. Okay, ballooning is a spectrum. It's part of the hepatocyte family. So you're really trying to identify bad apples from all the apples. You're not trying to identify oranges from apples. So that's actually this spectrum nature of ballooning made it intrinsically difficult to be reproducible. So what we did here is really, even for the human to go back, without establishing this threshold, even for whether it's a human or it's a machine, it's difficult to maintain this reproducibility. So what we do with the AI is that we are able to establish this threshold, and that's how we achieve 99%.
Dean, one of the things that Quentin was talking about this paper, actually, in the last conversation about Q2 ballooning, was the idea that, and this came from comments Stephen made about how he was trained, that really it isn't the balloon in a vacuum, that you tend to look and see how much likely you think it is the steatosis is there, and then if you think more likely, then you look harder, and then ballooning picks up some of that. When you talk about the range of variability for the individual going from 40 to 90%, particularly in the context of Joern's comment about not everybody is equally skilled or equally experienced in looking at the liver or looking at NASH. A, is that a major contributing factor, or how major a factor is that in the 40 to 90% range? Do you have a feel for that? And then B, what are the other factors that might lead us to understand why some people have higher concordance than others do?
First of all, I'm just explaining what the data is showing. So there are what we call basically overcaller and undercaller. So there are people basically continuously overcall a lot more than others. But at the same time, they are self-consistent. That means when we rotate the image, they still. So So I think that means they have a level of threshold internally. And I also want to highlight that we didn't have a communication, so the group didn't reach a consensus before this exercise. So this group of experts, they are relying on their past experience in order to do that. So they are very consistent with their level of threshold. So I think that's one of the contributing factor. So if we had this consensus discussion earlier, which is in the context of clinical trials, I believe they will reduce this error. But having said that, it's still not a perfect solution.
Okay, great. Other thoughts or other questions?
Yeah, I mean, just to extend what Dean was saying there, because one of the things we did in the paper was we tried to look, or, what is it that makes certain pathologists run hot and versus running cold in terms of their ability to see ballooning. So we actually looked to see, well, how much weight did different pathologists put on the size of cells? And there were clear differences there, that individuals who expected a very large cell always to be a balloon, necessary to be determined to be a balloon cell, tended to see fewer balloon cells. But if you were more permissive and said, well, a balloon cell could be quite big or very big, you tended to see more and more balloon cells. So there were certain patterns of behavior that were part of it. That was just a very simple example of one of the things that clearly contributes to this. And, as we mentioned, scores like SAF that do provide a little bit more definition of what is a balloon cell are potentially helpful in that respect when you compare it to how NAS is scored. Nevertheless, to my mind, because of the subtleties of assimilating all the visual clues to identify a balloon cell, I'm not sure this is just a case of training, because we had a group of very highly trained pathologists here. This is something where we need to provide an additional layer of assistance to really standardize, I would suggest. It'd be interesting to hear what Joern and Mazen think.
The thing that came up to me now listening to Quentin is, if it's not about the training of the histopathologist, then I guess there are no, even if you're highly trained, there are no clear rules, because there's no clear picture. There's not this one balloon hepatocytes. They do not, it's biology. They don't always look the same. I think that's what it comes down to. And then it depends on your personal experience, the amount of tissue you've seen over your career, and maybe other factors, whether you call it ballooned or not. So again, quantification versus semi-quantification, there is no yes or no answer to this, is what it comes down to me. And I think that's why it's so important to loop in the machine and augment the histopathological call. Let's say it that way.
No, I agree with you, Joern. And, we know that if you put the pathologists together and they discuss and they review images, they do harmonize for a while. But what we don't know is how long that tuning of the violin stays before the strings stretch a little bit and definitions begin to move away again. This speaks to the issue here. So yes, you can improve inter-observer variation, but even that doesn't necessarily mean that you've found the right answer. You've just got people to agree on a concept. So it is a really challenging area, this.
That makes tremendous sense. Mazen, you have anything you want to add or question?
No, actually, I have a question. And I probably should look at the paper into more detail. So, what was the final conclusion of the balloon side that you guys agreed on? Is it the consensus of the 9, or what are you carrying on in your machine learning model? How does the balloon cell look like?
Obviously, Mazen, there isn't a right answer to the question. So what we've demonstrated is that the more pathologists who agree that a given cell is ballooned, if you use only the cells where, for example, 7 pathologists all agree that they're ballooned, to train an algorithm, and this is what Dean modeled very, very elegantly, you will find that the algorithm is more specific potentially, but less sensitive. And so it's the idea, whereas if you train it with just every cell that any pathologist thought might be ballooned, you then have an algorithm which is much more sensitive, but much less specific. And so we selected a midpoint in the paper of a concordance of 5 pathologists because it was a useful point for discussion. The reality is here that what we've observed in this phenomenon in terms of how you can tune the algorithm potentially allows you to actually dial its sensitivity and specificity up or down according to to the question you're wanting to ask. So if you want to be absolutely sure that there isn't a single balloon cell anywhere, no siree, then you turn it one way. On the other hand, if you want to be identifying cells that the majority of pathologists, or in English law we have the concept of the man on the Clapham omnibus, which is basically the man in the street. So if we had the pathologist on the Clapham omnibus, then you turn it the other way and dial your sensitivity and specificity in that direction. Dean, I don't know, have I explained that well enough as a specialist?
I understood it well. I think it's brilliant. I do wonder, for the clinical trial purpose, I'm just thinking loud, if it will make more sense to be on the specific side than the sensitive side, because the sensitive side will, at the end, your drug will not work for sure.
Dean and I are both nodding like fools as you said that. We completely agree.
Yeah, exactly. So the idea is really, like Quentin keeps saying, is not to look for the absence of ballooning, but really to see the trend, the quantitative change that you can highly reproduce to verify the change. So, but then with the level of the compromised sensitivity in a way, but yet you get a very clear look at how the intervention is working.
So that's an important point, because this makes it a useful tool in a phase 2 trial, but not in a phase 3 trial. Because you're saying, if we're still stuck with the resolution of Nash picture on the drug approval pathway, it will be difficult just to show a trend downwards. But I think it's very important in a phase 2 trial where you want, a dose effect established and you want to see it goes to the right direction.
Actually, that's why we are working on the next part of the study, specifically trying to extend this to look at phase trial and even post-drug approval, what to do with this.
Yeah, and don't understand me wrong. I think it can help there, but based on what you say, showing the reduction, this is not going to be an approvable end.
Then the question becomes what the right way to use it in this kind of setting is, right? Obviously, you say phase 2, not phase 3, but to what degree, I guess I'm asking, were we talking about sample challenges in large populations and all that? Phase 3 is really where you spending money and time, right? So do we have any thoughts on, Dean, I know the paper doesn't cover that in Quentin, but do we have any thoughts on what might make phase 3 work better from this perspective?
So for right now, what we are working on is definitely, I think one thing is to correlate these into clinical endpoints. Basically, I think that's the best way to answer this question. Meanwhile, what we are trying to do is really another thing we're looking at, which is what we call colocalization with fibrosis. So this is actually something we are pounding now with steatosis and fibrosis as well. So what we have learned in steatosis is that when there's a significant reduction in steatosis, fibrosis changes not evenly across across the biopsy. So where there is co-localization with steatosis change, we actually see the changes more correlating to mechanism of action. So that's what we are looking into next. So this is actually where the AI can really help. As part of this paper, we actually identified that the ballooning index is some of them is actually fibrosis. That means pathologists are at some level, when they evaluate, they actually are affected by the fibrosis around a balloon hepatocyte. So when we actually later talk about it, the pathologists all acknowledge that, they are aware of that, despite this is not kind of part of the requirement for ballooning. So this is basically what we are looking into as well.
How do you colocalize?
What that means is you can actually see collagen wrapping a balloon cell. So that's actually something we actually kind of see, and in some cases there are some inflammatory cells in that complex as well. So we see isolated balloons and we see clusters of balloons, and in the cases of clusters you can see a very distinct collagen pattern within this cluster. They are wrapping balloon cells, which is not so much a kind of normal perisinusoidal fibrosis pattern we see in a healthy hepatocyte.
And is that where you see fibrosis, I guess, losing that cell or resolution of that ballooning? Is that the one that lead to fibrosis improvement?
So that's actually something part of the next phase we're looking into. Currently, in this current paper, we're establishing the concept. So these samples are no intervention. There are no treatment involved in the phase 1. So phase 2 is where we will bring this in.
So are you trying to say there might be variation in balloon cells in terms of importance?
The short answer is we don't know. For me, it's logical. Basically, is it single ballooning versus a group of ballooning? Which one is more important? Which one is more damage? Which can cause more damage?
I think that's fascinating, to be honest, Dean. It's kind of personalized medicine for the ballooning cell. So I look forward to your next step.
I mean, as Dean says, this piece of work that we've published now was necessary because of the variation in how ballooning is identified as it currently stands. We don't have a stable enough concept of a balloon cell to then be able to go on and look to see what are the ramifications, how does that influence pathophysiology, what does this mean? So the work that we've published here, beyond its relevance for the regulatory science, for drug development, is actually the foundation for a whole slew of further study to really understand the biology of ballooning and how it interacts with fibrogenesis and so on. And, as I mentioned earlier, potential to use it and, these sort of AI tools as a standard against which we can reassess omics data sets and so on. So it's a gatekeeper step to allow us to advance the field on a number of different fronts.
And when I think back of sitting down with my pathologists, they normally call out balloon cells and inflammatory infiltrates together, not so much the fibrosis bundles wrapping around which is very interesting because it speaks to, again, the regenerative response, and that could be a very different fibrosis band compared to a scar fibrosis band that's building up. I agree. There's so much interesting aspects that we could potentially learn on the pathophysiology, resolution versus progression and these type of things.
I have to say, one of the strengths of these techniques that Dean and the team have developed is that you're looking at the fibrosis and the ballooning in the same section because you're not having to use a different stain to pick up the finer fibrosis, for example, which immediately moves you a few microns away from the H&E section. I think that adds to the power of this. That's just my speculation, but I think it's worth remembering.
So let me note that I think in the last 2 minutes, Dean, you've just teed up another episode for later in the spring, which is what are we learning at this level and what does it tell us qualitatively through quantitative assessment about how the liver works and how we might think about all that differently. With that, let me just take a few minutes, turn to Mazen, and Mazen, ask you to talk a little bit about cirrhosis and your AASLD paper.
Yeah, I mean, this project actually has started many years ago. I like to sometimes read previous literature, and I went back, I think, as far as 10 years, and I was looking Lupe Garcia-Tsao work on hepatitis C, and the concept was she published in Cirrhotics, but what Dr. Garcia-Tsao was studying back then, that she's saying, well, the conventional histology looking at fibrosis might be missing few important elements of the cirrhosis architect. She started looking into few things in the cirrhosis architect, such as septal thickness, which we know it's very important in cirrhosis, and even in the NASH field. The JHEP paper by Zubair Younasi showed that more collagen and septal thickness, they define these cryptogenic cirrhosis people, that they are more likely to lead to outcome. So back to Professor Garcia-Tsao work, so they started semi-quantitatively, speaking of looking into septal thickness nodules, how many nodules you have in the cirrhotic liver, how big is the nodule, as well as the fibrosis area, which has been concept around for and studied in NASH through the collagen content. So in her work, she combined these three features: septal thickness, nodule features, and fibrosis area. And in few studies, she looked at if adding them adds value, and it did, but they were conflicting data, and they attributed the conflicted data into the semi-quantitative approach. And they suggested that's the reason why we're getting conflicted data, yet we still believe septal thickness, nodules, features, and fibrosis area are very important. And there was a landmark review by Lupe and Dr. Scott Friedman on that topic. So I think in 2017, or I don't remember, Dean, or 2018, I reached out to Stephen Harrison and Naga Chalasani, who are the PIs in the Galactin study, and asked them if we can look at that using in machine learning, and this is when the ball started rolling. And then Dean and his team got involved, and Dr. Zach Goodman started looking into multiple histological variables related to the septa, nodules, and fibrosis using these concepts. And the reason why we use the Galactin study, because as you know, it's one of very few studies that it had portal pressures, and we wanted to correlate this new kind of histological thinking to portal pressure measurements, clinically significant portal hypertension, as well as changes in the portal pressures by 20%, which, as you know, clinically significant portal hypertension and changes in them correlated with outcomes and an improvement in outcomes. So this is when the work started. It took a few years. There were about 450 something histological variables that HistoIndex identified in cirrhotics. The majority related to the septa, about 250, some related to nodules, about 20, and about 180 for fibrosis. So again, it's kind of redrawing the architect on histology for cirrhosis using what we call it septa, nodule, and fibrosis, SNOF, we call it the SNOF, or SNOF score, whatever you want to call it. So when we used each feature of machine learning, like the septa or nodules or fibrosis separately, they did correlate well with portal hypertension as well as clinically significant portal hypertension. However, when you put them together, the septa, nodules, and fibrosis features in a score, that was very reliable in detecting portal hypertension, clinically significant portal hypertension, with area under the curve of 0.85 and in the validation cohort of 0.74. Importantly, also from that study, we went beyond that. There were varices that have been developed or existed, either existed at the beginning of the study or developed throughout the study. So we looked at this SNOOF, or whatever you call it. It can distinguish the presence of varices or not, and it did actually. So the area under the curve for that SNOOF varices score was 0.86, and the validation was about 0.7 something. And importantly and finally, changes in the SNOF score correlated with changes of portal pressure of more than 20%, which a lot of people use as kind of measurement point to see if HVPG is changing, and it's distinguished that changes by area under the curve of 0.89. So in a way, that in a summary, that was going beyond the conventional histology for cirrhosis, adding important features using HistoIndex second generation method to look at important features, which is nodules, fibrosis, as well as septal thickening, and we correlated with important outcomes in clinical trials, such as varices, clinically significant hypertension, and changes in portal hypertension. So in a way, it gets validated more. You can go in the future and stop using portal pressure measurements, which we kind of stopped because it has been really difficult, but I'm still hearing this new trial coming with portal pressure measurements. So just imagine if that trial did not measure portal pressure and use this new technology, because it does have good correlation with portal pressure, and portal pressure changes, even varices. Of course, everything needs validation. It's hard to validate such a study quite a bit, because there are not too many studies out there that they measure portal pressures. And as you know, there was a similar effort on AI by other groups, but I think some of the features that we consider here were not considered in that paper, but we considered all major important features that our fibrosis expert looked at a decade ago.
Thanks, Mazen. That was fantastic and really, really, really helpful questions.
I'm going to ask a quick question, Mazen. Congratulations. very nice study also to just go back into the literature, see what's been done in the field, because sometimes I think we forget that. We can learn from previous great minds that have looked at that. I'm a little concerned that you have a lot of collinearity in your score, because my understanding of progressive fibrosis in the liver is you get thickening of septa, you get nodules, and I would expect that in the presence of nodules you have more portal hypertension because you really have the scarred off tissue and so on. So I'm not sure in the presence of nodules. I guess my question is, I'm not challenging the data. My question to you is, how much does the bandwidth then or the fibrosis septa information add if you have already established nodules? And maybe I'm not sure you had the chance to look at that, but that's just, thinking about it pathophysiologically. Where does the SNOOF add in here?
Thank you for this question, Joern. So, and Dean, maybe you also can, I would like to have your input. I mean, to get to this score, as I mentioned, we evaluated each one of them separately, and they performed well. And then through statistical methods, we found out of all the features, as I mentioned, there are 250 features of the septa, for instance, and we picked through statistical method the best ones that will improve the outcome we're looking for. And the septa did add accuracy to the nodules when we combined it in the SNOOF score. So I don't know if that answers your question, and I'm interested in Dean's thoughts as well.
Actually, in cirrhotic samples, we realized that a huge collapse. So you can have one big chunk of portal tract. You can probably spot like 5 portal tract or string together. There's no more tissue, everything collapsed. So we actually had a problem kind of establishing, is this a big portal tract or is it a septa? So how to properly define what you say septa width? And bear in mind, this is a needle biopsy. So you also kind of limited by the size of the needle itself. For example, the width is probably as far as we can measure. So this is something that's very interesting we're actually trying to do. So when we do this correlation, what Mazen described, we didn't dig in too much into that. And I think it's a very interesting question. We should actually really expand more into looking into this septa versus nodule.
Yeah, again, and also because of thinking that, the type of septa, the thickness and the structure of it could address, is this really something that's on the way out, progressing or regressing? That's something that I'm very interested in, and particularly important in drug trials, of course.
Great.
Let me run with that. I'd like to, in the time we have remaining, ask you a question. You say in the context of clinical trials, how do you see this work? You made the comment before about phase 2 and phase 3 trials. What do you see as the impact of this work on clinical trial conduct today? And if you take the research down a couple of steps in the direction that Dean has described, how do you think it might affect trials then?
I can take a jab at it, and then maybe others. As I said, this is a work that has been done in one trial. As I mentioned, there's another work from the simtuzumab, kind of the same concept. I think both are great work, but this one in particular had the key features that the fibrosis experts have talked about before. As you know, like cirrhosis is a beast, and cirrhotics trials have been very challenging. So I'm a total believer in the cirrhotic trials. Whatever you're looking for, you really need machine learning and artificial intelligence, because this conventional thinking that we need to go one-stage fibrosis is great if we can get it, but it can be very difficult, and we could be missing a lot of fibrosis changes in cirrhotics just by looking at this conventional one fibrosis improvement. So measuring collagen content, measuring fibrosis in more details, especially in the cirrhotics, is very important, because as you know, in cirrhotic trials, 1, you need a very accurate assessment of what's changed fibrosis. 2, you need a good duration for fibrosis to change if the drug is working. And if you have an accurate tool showing every single TDES and fibrosis improvement, that will be very important. Now, in terms of this paper, since it did correlate, these scores correlate with existing of varices, changes in portal pressures that we know historically they correlated with outcomes, I think you can start looking into these scores in such cirrhotics trials and their histology and see if they are moving the needle and eventually connect them to outcome, to just go beyond the conventional thinking of what should be done in cirrhotic trials, because those are the trials that we still don't know a lot, and we still don't know how to approach them to show improvement other than outcomes are, of course, the best thing you can look at, but it's not easy to do outcome studies. So if you want to go for histology, I think you really need more details in terms of fibrosis changes and their relation to outcomes.
Just to add quickly, and I totally agree, Mazen, I think if you were looking at fibrosis regression, you're going to look at those very early cirrhotics that are difficult to find, and then you are in an arena where some are F3 and some are F4, and the biopsy might not categorize them correctly. And I think that's also a danger in that field if you're only looking at fibrosis regression. So I support the notion that there is additional information that needs to be explored in the cirrhotic population.
No, not to mention also in cirrhotics, most people gonna try to treat or start treatment with the compensated cirrhosis because they are easier. But we know that these compensated cirrhotics are not one bucket. They are probably different levels of compensated cirrhotics and different severity. And that has been talked about before by Garcia et al. and Friedman. And actually they use this approach to subclassify the compensated NASH cirrhotics. So it will help teasing out could be different severities of compensated cirrhotic and target the right population for a certain MOA.
Okay, great. So I'd like to thanks, Mazen. I'd like closing thoughts and more broadly. Okay, although I guess we addressed this in the first conversation a lot, less than the second one. The aggregate impact of what we've been talking about here, the use and some of what we've learned about the specific nature of the use of AI. In the conduct of clinical trials, we just talked about cirrhosis, but maybe more broadly. And then B, in the conduct of the ongoing evaluations about the kind of things that Quentin, that you're doing around NITs and AI histopathology, and where you think that will fit in the clinical trial architecture of the next few years. Let me start with Quentin on the clinical trial question, then I'll go back to whoever would like to answer on what will it mean for trials themselves? If we think about the various things, for example, the nimble work and all that, right? We're trying to do a better job of correlating different non-invasive measures and histopathological measures to get to outcomes and a better understanding of what we capture in a clinical trial. I'm wondering the specific ways in which you think this work will push us ahead.
Yeah, no, I think that's a really good question. And this comes down to the crux of the matter. So if we think about the current trial paradigm, Roger, obviously we use a biopsy as an accepted surrogate because we believe it predicts cirrhosis, which we in turn believe is going to be predictive of hard outcomes. What we are doing in Litmus and also in the United States in the NIMBLE consortium is we are trying to identify non-invasive biomarkers that may be able to do many of those same things that histology can. But at the moment, we're working by basically comparing our non-invasives to histology. And the problem there is that without a standardized read for all the reasons of variation that we've been talking about here, it means that we're comparing a non-invasive test that might be highly accurate to a potentially less accurate, or at least one of the first things here and one of the immediate applications for this sort of work is to be able to standardize our histological assessments as the reference point for the further development and validation of non-invasive biomarkers. And it's great from that point of view that within Litmus, Dean and the HistoIndex team are one of the partners in that consortium, working with Joern and myself and all the other partners, specifically so that we can start to do that and to improve our histological standard and therefore improve the reference point for the development and validation of non-invasive biomarkers. So as we fix the histology in terms of inter-observer variation, we're going to both help ourselves develop better trial endpoints and also help ourselves develop non-invasives that can support drug development in the future. So it's a double win, really.
Okay, other thoughts in terms of the question of where else we might be taking this in the context of specific clinical trials as we do the kind of work that Quentin just described?
Yeah, I guess, remembering the first conversation we had here, and my question to Quentin is I'd still like to see a compound score looping in some of the biomarkers, as Quentin stressed, and those technologies, and really come up with a full picture of something that cannot be captured on liver histology by itself, and putting patients into buckets based on those multiple assessments we gain so much knowledge on these days.
The NASH A1C, that's what you're thinking about?
Yeah, well, if only it was that easy.
I know.
I think to Joern's point, and we're already seeing this with NITs as we begin to leverage proteomics approaches, transcriptomics approaches, we're understanding that it's, again, a complex disease and that a single index, a single blood test, a single measure analyte is unlikely to be the answer here. It is likely to be a multi-analyte panel to most accurately characterize it. And if you think back to the meta-cohort data that Litmus presented at EASL and ASLD last year in various different forms, it's striking there that it's some of the somologic biomarkers, which of course those panels include about 35 different proteins, were some of the better performing ones, certainly outperforming simple scores like FIB4. So we're already beginning to see a graduation, and that the more you include in your model, potentially the greater fidelity it has. There'll be a limit to that, but it is an interesting phenomenon.
Okay, and then let me ask that question to Dean. So where do you see this heading in the context of supporting trials better and also a better understanding of the way to improve our methodologies over time?
First of all, I agree with what you said earlier about shrinking the semi and really going in quantitative. Another thing is that the current histology assessment is kind of limited by the category system, the NASH-CR, and you eventually record it as a category 1 or 2 or 3 or 4. But in fact, what's being described is morphology. We've been talking about the perisinusoidal fibrosis. So it's really to actually enable you to quantify morphology, which was really the intention of the system at that time. So this is another level which I think we need to put a lot more effort into it, because right now people the whole 1 point reduction is actually a consequence of that. But the fact is that we see the features reduction, like what we don't say about the facts. You have different septa. One is indicating progressing, one is indicating regressing. We see it all the time. I think everyone sees it, and they believe, they are convinced that's what's happening. AI can really come in and help to really address all these subtle changes in a fully quantitative, fully reproducible manner. And this really is a powerful tool for the drug development.
And now, back to Roger.
This conversation is sponsored by HistoIndex, the world's leading specialist in stain-free AI digital pathology solutions for NASH clinical trials. Join HistoIndex for its complimentary webinar, Deciphering NASH, Fibrosis Dynamics in Cirrhotic Patients and Insights into Balloon Hepatocytes Using AI. That's a mouthful. At 11 a.m. Eastern Daylight Time on Tuesday, March 23rd. For more information about that podcast, visit the Season 3, Episode 14 or HistoIndex sponsored pages on the Surfing Nash website. We hope you've enjoyed this recording. If you have any questions or comments about the content of this conversation or the entire episode, please send an email to questions@surfingnash.com. We'll be back next week with a review of high points from the Nash Connect and Liver Connect meetings. Until then, stay safe, surf on, see you on the podcast. Bye-bye now.